Where we left off last time was talking about Java monitor objects, so I just wanted to finish off a discussion of some of the usage considerations for using them effectively. In particular, we'll talk about some of the common traps and pitfalls of using built-in monitor objects. And these are almost always relative to alternatives like condition objects and reentrant locks. So there's a bunch of issues with monitor objects you have to be aware of. One of the things, first and foremost, with a monitor object, it's a limited capability. It doesn't have as much expressivity as using condition objects directly. One of the things it doesn't have is it doesn't support non-blocking operations. You always have to block to get a monitor object when you do a synchronizer, when you use the synchronize keyword. It doesn't support timed access. You can't interrupt it. So there's a bunch of things that you would get with a reentrant lock that you just don't get with a monitor object. The synchronized statements only support scoped locking. And what that means is that whenever you come into a synchronized statement, no matter what the heck happens, the lock is always released at the end of the block. And it turns out that that is actually inefficient for certain types of concurrent algorithms because it requires potentially redundant checks for internal states. I'll show you an example of this when we go over the assignment 4 skeletons here later this morning. And you'll see some examples of where that becomes a problem. There's also no sensible support for timed wait operations. This is something, if you were curious about this, take a look at this link. The wait operation doesn't return a value. The timed wait operation doesn't return a value that indicates what happens. And so as a result, it's very hard to tell whether something timed out or not. And there's weird sort of hackish workarounds for that, but it's basically a limitation. And that's yet another reason why they added condition objects, which do have sensible return values to indicate whether something timed out if you use a timed wait. There's also only one wait queue and one entrance queue. We talked about that before. That's one of the main limitations with a built-in monitor object versus things that you would get with using condition objects, because you can have multiple things. One of the consequences of only having one of these wait queues and one entrance queue is you can have what's called nested monitor lockout. You can read about it down here. Here's the problem in a nutshell. Let's take a look at buggy lock. This is a little class developed purely to show off the problem here. And we've got some object called monobj, which is just an object. And we have a Boolean that keeps track of whether something's locked or not. So here's the lock method. The lock comes in here. And notice it's synchronized. So that means that the intrinsic lock must be acquired when lock is called. And then while m locked, while this value is locked, we're going to synchronize on this nested monitor and monobj, and we're going to call wait on that. Now the thing to remember here is when we call wait on this nested monitor object, that will release the synchronized intrinsic lock on n or m monobj, but it will not release the outer intrinsic lock. So that will still be locked. So we'll be waiting here. And down here, if someone comes along while we've got this lock call held and calls unlock, then this synchronized statement still applies to the intrinsic lock, and therefore this thing will never get a chance to run. So this is what's called nested monitor lockout. And it's a weird, strange quirk, and it's some of the semantics of monitor objects. And the other thing that you don't have here is you don't have the old two-lock queue optimization that's built into linked blocking queue, where linked blocking queue has a pair of locks which distinguish between taking something out of the queue from the front and putting something into the queue at the end. And a built-in monitor object doesn't really let you do that. Okay, so those are some of the problems. It's limited, doesn't have all the features that you come to expect with more advanced uses of monitors. Another issue is choosing between notify and notify all is tricky, and this is largely due to the fact that there's only one monitor object, or sorry, one monitor condition per monitor object. And you can read about this here. It's very, very subtle. So here's the issue. you'll have to use notify all most of the time. And you can only use notify if two properties hold. This should say conditions. This should say properties, not conditions. So one of them is uniform waiters. That means everybody who waits on the monitor object waits for the same condition. And that turns out to be problematic because you only have one monitor condition per monitor object. And the other thing is one in and one out. So notify will only have one thread go at a time. So the rule of thumb is try to use notify wherever possible to avoid the so-called thundering herd problem. Remember, the thundering herd problem occurs when you wake up everybody who's waiting on a monitor condition, but only one thing can proceed. So you wasted everybody's wake-up time to do nothing. Only one guy can go ahead. However, you typically need to use notify all since there's only one wait queue. And it just becomes a mess. There's also another issue, which we're going to talk about in more detail in a second, having to do with fairness. So the way that built-in monitor objects work is the specification doesn't dictate which thread or threads get awakened when you notify something. So if there's a bunch of threads that are waiting, we don't know which one is awakened. It's up to the virtual machine and the operating system and so on to decide who gets to wake up. And this is what's frequently called haphazard notification. It's not really haphazard from the point of view of the underlying scheduler, which makes decisions hopefully based on good reasons like thread affinity or other caching-related properties. But from the point of view of an application, it's haphazard. And the way to solve this, or a way to solve this, is to use something called the specific notification pattern, which you can read about at this link and which we're going to cover in more detail momentarily because it's what's going to constitute the final programming assignment. And what happens here is you can program things to programmatically choose a particular thread to run from a set or family of waiting threads. And you'll see that you can do it in ways that do stuff like obey FIFO orders. So because of all these limitations and drawbacks and non-optimality properties and so on and so forth, the monitor objects that come built in are often insufficient. So that's why there's other stuff, right? So we've got all the other concurrent locks, like reentrant lock and condition object. We've got other mechanisms altogether. And so Java gives you a range of things to choose from. That's the good news. The bad news, of course, is you have to figure out which ones to use, which is sometimes tricky. But the main ones are reentrant lock and condition object. And a very common thing to do is to have multiple conditions to handle the fact you're waiting for different types of things. Android also provides a whole pile of stuff. You've learned about some of them, most particularly async tasks, but there's other stuff it provides as well. And one of the neat things about the abstractions that are provided by Android in the form of these concurrency frameworks is they use message passing as opposed to synchronization and coordination. So coordination is handled by passing messages which can be passed between threads. So a lot of the subtle low-level issues that we've been talking about kind of go away, and it's handled for you internally by the Android concurrency frameworks. Okay, so that's the quick overview of usage considerations for Java monitor objects.